bigger waters. Anybody? It's going to be you.
So it's an act that passed in 2012 to make changes to the way the National Flood Insurance Program is funded, where basically this insurance program is billions of dollars in debt from payouts during hurricanes Katrina and Sandy. And this act was proposed to try to remove some subsidies or increase rates for a lot of residences that are in really high-risk flood areas. So basically make their payments be more proportional to the actual risk of flooding that they're experiencing. And so they actually passed this act with a pretty wide support. And
then stop. So that was great. You stole half of my thunder. So I'm gonna leave. I'm gonna keep a little bit of it. So right, it's the Bigger Waters Flood Insurance Reform Act of 2012, passed by the Senate and the House, signed into law. And just the visual for the week is this, which is actually one of FEMA's new flood maps. Does anybody know where? Can you recognize that area? Close by, but it's not Ithaca. All right, it's Binghamton. So you can see the Susquehanna River here coming through. And sort of the obvious question is, what do you notice about a lot of this potentially inundated land? This is the 100-year floodplain that they've got highlighted. What do you see throughout all here?
Buildings.
Buildings. People like to build there.
Flat.
It's flat. So it's not really unusual. This is sort of the case in a lot of cities that are built right up against major rivers like this that are prone to flooding, and the Susquehanna certainly is one of them. So again, as Lauren described, it's an extension of the National Flood Insurance Program, which has been around for a long time and actually has been doing pretty well. What essentially happens is people who live in the floodplain get a bit of a subsidy for people who don't, and even when there is a flood, so there might be a lot of damages that don't work out so well for the subsidy that year, but provided there's enough time before the next flood occurs, you have some time to rebuild some of the money inside that program. So So this program was working out well until Katrina, Irene, Lee, and Sandy all hit within 10 years, and so it sent them, I believe, about $30 billion into the red there. So that was a lot of money to make up, and they needed to do something, which is why they came up with this Bigger Waters. So what's interesting about this, so the news of the week part comes in, is that in January the Senate actually came up with and passed an act by the name of, to delay the implementation of certain provisions of the Bigger Waters Flood Insurance Reform Act of 2012 and to reform the National Association of Registered Agents and Brokers and for other purposes. They voted on that act and the Senate passed it, which essentially delayed the Bigger Waters Reform Act of 2012 for another 4 or 5 years. I'd have to look at the details, but that was the essence of the act. The act to delay the act, which the Senate passed. This week, the House is also looking at delaying this Bigger Waters Reform Act, although they delayed voting on an act to delay the act until next week. So, who might be in favor of the Bigger Waters Act? Who does that actually help?
People who don't live in flood zones?
People who don't live in flood zones. It sounds like pretty common sense if you're saying that to subsidize people who live in the floodplain where we know these types of storms can happen and potentially cause a lot of damage, why are we subsidizing these buildings in these areas? Who's not so happy about this act? The people who have those buildings or who have to live there. A lot of times this might be, they can be poor areas, people who move into older homes, who just happen to be in the flood zone. There's not always a lot of options in some of these places. So it is a very controversial issue. The reason why they're delaying the act is because so many people got angry about the possibility that their flood insurance was going to go up sometimes several-fold within the next couple of years. So, I mean, what do we think about this? This is a pretty major act. The Senate has already decided to delay it for at least 4 to 5 years. The House delaying it. Is this a good policy? Should we try to do something like this? Does this make sense? Any comments?
Yeah, there was an interview on CNBC this past week with Warren Buffett saying
What did Warren say?
they made so much money off of storm insurance, the insurance industry.
Mm-hmm.
Even with all the hurricanes, there's no way they haven't made a lot of money. Because they hadn't had any hurricanes for a long time that were of significant storms. And so you said that the private insurance companies have made a lot of money.
Private insurance companies, right? But this is public funding.
Right. So
program.
that's an argument for why how does the public do? Presumably there were years and years in which they should have been collecting insurance in which they had very little money that they had to pay out.
Right.
But my guess is that money.
Doesn't it seem though that if you were a private insurance company, you would realize that this is not actually the area where you're going to make very much money right in here necessarily.
Or you charge
you wouldn't
more.
sell them insurance there, or you would charge them more than they're able to afford, which is why they were getting this subsidized public insurance in the first place.
And it sounded like one reason there was a lot of support initially was because a lot of people thought it was mostly affected people with second homes, on the Outer Banks who could,
Right.
who can afford to deal without the subsidies.
Yeah.
And then like these maps showed up and people realized, whoa, this is going to affect a lot of people.
Right. So the details of who these increased rates actually affect are a bit more complicated than what I'm making it sound like. It's not everybody, and there are tiers, and there's a phase-in and things like that. But it happens to coincide with a time when FEMA decided to, well, they needed to redo some of their flood maps because what the 100-year flood zone is changing. And so, yeah, more and more people found themselves in that flood zone, and so more and more people got angry. Anything else? Any other comments on this one, or thoughts? Does anybody have a home or own property downtown, maybe near Wegmans? Because when Ithaca's new FEMA maps come out, there's going to be, there's areas in Ithaca that certainly would fall under within the 100-year floodplain. So this definitely impacts a lot of people, not in just places like Binghamton, but also in Ithaca.
You've got to remember the alternative, which they don't have flood insurance, they get flooded, then the government bails them out anyway.
Right.
That's possible.
Right.
Yeah. All right. So that was today's infrastructure news of the week. Today's speaker, Jery Stedinger, comes to us from civil and environmental engineering. He works on statistical issues in hydrology, flood risk, which is why I tried to make this news bit relevant, and optimization of water resource issues and systems. He's also the chair of the Water Resources Institute Steering Committee, so we see quite a bit of Jery. And I'll get this down for you, so you can get your thing up. All right, Jery, it's all yours.
Okay, so they asked me to come up and talk about uncertainty, including uncertainty in evaluation of infrastructure for water resources. And this is an area I've been involved in for a number of reasons for a couple of years, and I'll sort of explain that. And because of that involvement, I called it an adventure story. It had to do with the U.S. Army Corps of Engineers, for the most part, trying to include what they call risk and uncertainty into their evaluation of flood risk management projects. And so a lot of things we were confused about in terms of what the implications were of doing different things, and some of that confusion has resolved itself, and some of it hasn't. And so this sort of describes the places from which this talk is drawn. It got started really with me in '95 when I was on a National Research Council committee to look at the way the Army Corps of Engineers was evaluating Auburn Dam. And so above the city of Sacramento, which is the capital of California, which is what, by economic measure, something like the 10th largest country in the world, They currently have a risk of 1 in about 60 or 1 in 70 of flooding downtown Sacramento. And the pictures of Schwarzenegger swimming over to the Capitol are really cute. And so the Corps of Engineers had proposed a dam at Auburn to be above the Folsom Dam, providing more flood protection. And after they evacuated or developed the foundation for that dam, they discovered that the proposed largest concrete arch dam in the country was right at straddling an earthquake fault. Decided that was a dumb idea, and anyway, there's a lot of pushing and shoving, and so they asked the National Research Council Committee to look at the Corps' evaluation and try and get rid of the claims that that was done poorly. We were sitting there minding our own business trying to write this report, and the Corps of Engineers came and said, hey, we've got a new idea how we're going to do risk and uncertainty analysis and putting that in flood risk management project evaluations, and that's going to be wonderful. And we sort of like, well, what do you mean? This was supposed to be an easy committee, and we were going to be out of here, and now you're telling us you're rolling out a whole new methodology. That was sweet of them. So we had to evaluate that, and I remember one of my favorite lines was they were describing this to us and how they're going to do it, and they said, okay, do you have what you need to know? And I sort of looked at it and said, look, I can't write a report critiquing what you've done based on oral history. I mean, you're going to have to give me a report, so at least I've got something to point at. There was a lot of confusion about what a lot of that meant, and I actually wrote a paper that got a Best Paper of the Year award, trying to understand what the expected probability of annual damages were about. We wrote another paper, I'll show you some results from that, trying to look at the implications of including risk and uncertainty in the evaluation and what that would buy. As the Corps rolled this whole procedure out, they had another National Research Council committee that was supposed to look at it in 2000, and I was on that committee as well. I was the only holdover. And then in putting this talk together, where I've given other places, the whole thing is really about how we do flood risk management and what we want to consider and how we try to do it well. And the neat thing about that, I like to refer to the Galloway report back in '93 after the Mississippi flooding. They wrote a report that tried to look at how we should think about our paradigm for flood risk management. And so that was the White House Interagency Floodplain Management Review. And I caught a couple of General Galloway's presentations, and so I've stole liberally from that whenever I could. And there's lots of acknowledgments because I had a lot of committee members who helped me out and write this, and some graduate students and other people, and so they all get credit for contributing to an effort to try to understand what the implications were of the Corps, including uncertainty analysis in their flood risk reduction projects. And so this was the first '95 report, and this was a 2000 report, and then in between I got thrown on another report for the American River arguing about how to do the flood frequency analysis. And so it's sort of that experience that contributed to this talk. This is truly an inspirational cartoon. It says, meaning statistics were up 1.5% this month over last month. And really, as we moved into this risk and uncertainty analysis, lots of people had lots of good ideas about lots of new statistics we could compute that were going to tell people all sorts of things. And I at one point sort of said, I just don't believe it. I'm not sure, how are people really going to use these numbers that you're generating? And the response was, well, I don't know, but I'm sure they'll figure it out. So if the people who were generating didn't know what to do with them, I'm not sure what anybody else did. So here's an outline of the things I brought, and if we don't go through all of it, that's okay. I can certainly cut out some of the later topics, but certainly the middle part is what I was supposed to talk about, so we'll get through that. But I like to start with Galloway's vision of flood risk management, and Brian was kind enough to point out what a high priority this is. And I'll just add to Brian's talk, I couldn't believe it. I went to a floodplain managers conference in San Diego, and a guy that was there from FEMA, and he spent the whole time telling people how they could get cheap rates. And it's like, wait a minute, you're for the federal government. Shouldn't you be worried about getting honest rates, not showing them how they can get an exception here, an exception there, and grandfathered in? When the federal government gets involved in that sort of thing, it often looks like there are opportunities to do nice things for the constituents and make everybody happy, and the general taxpayer pays. But anyway, the Corps of Engineers wanted to move from their traditional paradigm for evaluating flood risk management projects to including risk and uncertainty. And what you need to understand is that when any community in the United States pretty much decides they're concerned about flood risk,
they turn to the U.S. Army Corps of Engineers, and they have a budget from Congress to do flood risk studies, and it's highly subsidized. So if you're a community, why not take the Corps of Engineers consulting at half price as opposed to hire a consultant? And then if the Corps does the study, there's a subsidy for putting in infrastructure they'll build and all sorts of other things, and there's contribution from the locals that they have to help out, but it's quite a deal for the locals if the Corps of Engineers decides the economics, the public welfare improvement justifies the cost. And they were concerned that their analysis procedures should be improved. And this was not something they discovered out of the goodness of their heart. OMB looked at some of their levees and said, they're building these levees and there's 3 feet of freeboard on top. What's the benefit of that? And they said, well, there's not really a lot of benefit, but it's required. What do you mean it's required? Well, our regulations here require we put 3 feet of freeboard on the levee. Well, why do you do that? Well, you know, it's a safety margin. So what's the benefit of that? Well, it's required.
Can you tell people what freeboard is?
A freeboard means that if you have the 100-year flood and it's at the elevation of the rivers at 15 feet, then they would build the levee to 18 feet so that there would be 3 feet of freeboard. And in truth, that was to cover settlement, bad surveying, waves, the rivers going around this turn, and so they called it freeboard. And the OMB thought it should have some value, and they said it was required. And so their solution was, well, it's there because of uncertainty and things, and so we'll explicitly include uncertainty in the analysis, and that will get rid of that problem. And so anyway, that leads to some concerns about what the impact is of throwing uncertainty into the analysis, and whether or not the economics then is honest, and some discussion about uncertainty in design and what all that means. And it did say an adventure story, which means it was quite an adventure. And if I'm not confused at the end of this talk, that would be great, because you can explain it to me. I'm still confused. I'm particularly confused about how to explain it to people. But this is the cover from the Galloway report in '84. Brigadier General Jery Galloway, and it was called Sharing the Challenge, White House Interagency Floodplain Management Review Committee, and it was really nice. It said the same thing people have been saying before, but it said it very well. At a March '96 talk, General Galloway indicated the review committee was asked why there was widespread flooding in the upper Mississippi and Missouri basins in 1993. Does anybody know why there was widespread flooding in '93 in that basin? My mentor, Walter William, was asked why they were having a drought in Binghamton. He said, because it hasn't rained, and here the answer is because it did rain. But there are other contributors. The Midwest flood of 1993 was a hydrometeorological event unprecedented in recent times. It was caused by excessive rainfall. So at some level, it's pretty obvious. The loss of wetlands and upland cover and modification of the landscape throughout the basin over the last century and a half significantly increased the runoff. Most losses occurred prior to 1930, but some are related to more recent changes. People want to blame the Army Corps of Engineers for these things. Anytime something goes wrong, it must have been something a federal agency did. But in fact, the development of farming in that area, the changes in putting in tile drains, the removal of the grasslands that have been there, all contributed. There was also a straightening of the channel and some other things, and all of that had happened quite a ways earlier, and then we had a big rainfall event. During the decade ending in 1993, average annual losses in the U.S. for floods were exceeded $3 billion. We hear about Katrina and Irene and Sandy. These are big ones, but there's lots of small events that happen all the time in different places and cause damage, and people like to crowd the floodplain. Then when they get a flood, they get wet, and people have to argue about it. Galloway in '93 at a presentation said some interesting things that were pithy and actually true. Water runs downhill and ignores political boundaries. Water rises and it will happen again. And the last one here is, both of these are really frustrating because politicians love to play with the facts, and they like to think, people like to think it happened once. Everybody knows if the 100-year flood happens this year, when's the next 100-year flood going to happen? 99 years, right? Well, and it's an act of God. God wouldn't do that to us again. It's not a very constructive attitude from the point of view of flood risk. In my class, our students went through this, and if the 100-year flood happened this year, then most likely time for the next 100-year flood will have to happen is next year, because it's the most probable time, and so, anyway, so here's Galway. Human activity in the floodplain will continue. The idea that we should abandon the floodplain is just not realistic. Boats, harbors, lots of activity really makes sense along the floodplain. It's a beautiful place for parks and things, but when I moved to Ithaca, I thought, what a smart group of people. They put a park in the floodplain down at the end of the lake. They also put a high school and a middle school. But it was cheap because they got big playgrounds there, a lot of land. And actually what floods them is not that, it's the creek that comes down in the winter and it ices up and clogs the channel and they flood the high school and the middle school. But anyway, but with clear understanding, we're going to continue to be in the floodplain, but with clear understanding that any activity is subject to residual risk of flooding, and the costs of this risk should be borne by the sponsors of that activity. Brian, what about that bill you just told me about?
Yeah.
Should the people who choose to live there and put their house there bear the cost, or should the general taxpayer pay it, and they live there and they're stupid and are doing an economic calculation of their own, and we're subsidizing them to do stupid activities. All new activity will be evaluated for its economic, social, and environmental impacts and its effects on other activities in the floodplain. This gets into the fact that sometimes you can put a big building in such a way so as to clog the floodplain and increase the stage when a flood occurs so that other people get experience more flooding, and he's saying we should be careful not to do that. But anyway, that was Galway's vision. We're going to be in the floodplain. Let's try to do it in a smart way, and that means making people pay the cost so that we don't subsidize. All right, the Corps of Engineers wanted to do risk and uncertainty methodology, deal with this freeboard problem and OMB, and so here's what they sort of said about it. Risk and uncertainty are intrinsic in water resources planning and design. For a risk-based framework, an approach to evaluation and decision-making that explicitly and to the extent practical, analytically incorporates considerations of risk and uncertainty. And they have lots of good words and very motivational and talking about how this is going to solve everything. They used to talk about a level of protection, so they were going to design for the 100-year flood for their levees and then put a 3-foot of freeboard on top of them. And so there was this whole thing that you had a design event, 50-year flood, 100-year flood was what was used for floodplain planning, and they were not going to use that term anymore. In fact, they were going to try and add all these uncertainties into to the mix, and then they would talk about, this was great. So for levees, they were going to talk about whether the system was 90% reliable at being able to pass the 100-year flood. And it turned out most of that 90% reliable was because they didn't know what the 100-year flood was or uncertainty in the parameters. So we don't know what the 100-year flood is, but whatever it is, we're 90% reliable, we can pass it. And you've got to ask yourself if that's clearer than saying, taking all the uncertainties into account and their variability in hydrology, we estimate there's a 1% chance that this levee will be overtopped. Instead, we have a 90% reliability, which is a conditional non-exceedance problem for, you know, I haven't put a lot of that in here, but anyway. So that's what they wanted to do. Talk about level protection. Levee freeboard is replaced by a probabilistic description of levee performance. So they're not going to have this argument with OMB about whether 3 feet of freeboard is adequate, which really seems stupid because they had that same requirement regardless of whether the levee was 25 feet tall or 10 feet tall. Last. Risk-based analysis enables risk issues, uncertainty, and critical data and information to be explicitly incorporated into project formulation and evaluation. Okay, it was so funny. The Corps came in and told us we were going to do all this, and in '95, and I'm sitting there with Ken Potter and Bill Kirby, some other people who were outstanding in stochastic hydrology, and our draw drops, and we look scared to death. And there's this geographer there who says, "What's the matter with you guys? You've been telling people for years they should do this, and now they're doing it, and you look scared as ghosts." Well, I didn't have a lot of faith they would do it well. I mean, it's one thing to include parameter uncertainty in, but did you model parameter uncertainty well? You're describing with distributions what parameters can be and what could happen. Are those cases realistic? Are you capturing the realistic cases? And I think to this day, I never got them to adopt this diagram. You find it both in '95 and 2000 year NRC reports, but it's like, okay, what are we doing here? What's the computation that allows us to figure out what flood risk is gonna be. Oh, I can't walk over here. Okay, so this is a diagram, that was in the 95 and 2000 report. We said, well, what happens? First thing is there's possible values of the annual flood. So we're gonna describe the world as producing one annual flood every year, and if it's really big, it's gonna cause trouble. And so here is a tree that says there could be different values of that inflow flood, and we have a distribution for that. And we were looking in 95, particularly at Natomas, which had one big reservoir, not Natomas, Sacramento, which had one big reservoir, and that was Folsom. And so it turns out that the maximum flow that's going to come out of Folsom is not deterministically determined by what the inflow is. It depends on how the operators operate. And so if they've got a forecast that says things are going to be much worse, they may release more water early. 86, they really messed up. They forgot there was a coffer dam upstream at Auburn that failed, and they forgot about that. So when it failed, they got a real surprise. So possible reservoir operations determine outflow peak for any inflow peak Q. So we allowed some variability there, which was something they wanted to do. Then this outflow peak goes out of Folsom and through the levees by Sacramento and Natomas, one on each side. And so here's the reservoir outflow, and here's the downstream stage. And it turns out there's some nonlinear some dynamics in the whole flow routing. There's uncertainty here due to parameters in the channel that maybe aren't calibrated. Turns out temperature changes the density of water, and that results in some variation. So there's a curve here that looks deterministic, but one of the things they're going to go back and do is put uncertainty in that. They're going to say, we're really not sure. And now, the inflow flood here is random, but we don't know the parameters of that randomness. So when they talk about uncertainty, one uncertainty is going to be to add uncertainty to this line. Another uncertainty is to play with this whole distribution. So anyway, we've got an inflow flood, goes into the reservoir, comes out, outflow gives us a stage. If the stage is big enough, the levee breaches. Does the levee breach when it's overtopped? When it almost gets overtopped and it hits all those holes, the rodents left in it? Or can it take 6 inches of overtopping? Or has it settled? Or was it like New Orleans where they all just pushed back before they got to the top because they were so poorly designed and built? So they are assuming that the geotechnical engineers will give them a probability for every levee as a function of stage that it's going to fail. And in most cases, they gave a lower bound where there wasn't any failure, an upper bound where there surely was a failure, and they sort of linear interpolated. And I don't think we added any parameter uncertainty to that. Or is that uncertainty? Is there one level at which the levee fails and this is uncertainty? Or is there variability in the levee depending upon whether they've done repair recently? How many people say that's variability? How many people say it's uncertainty? How many people don't know the difference? Well, that's the problem I have. Anyway, and so when they put all these together, they're going to get a damage distribution here, and here is a probability distribution for damage without the levee, and here's the distribution with the levee. And so it's the stage alone used to estimate damages. It says, okay, so I got that wrong. So as a function of the stage in the river, this is the expected damages, and with the levee, it doesn't fail very often, so you have it's much lower than here, which is without the levee. Dotted line is without levee, overtopping, or breaching. It's got to be, it's lower. So anyway, so this was our way of trying to say, because they're going to compute expected damages, and then they want to tell people this is our expected damages, but we're uncertain about that. And why you're uncertain? Well, we're uncertain about it because we don't know what the flood distribution is. We don't know what the stage discharge relationship is. This they're going to pretend like they know that. It's random, but they're not going to include uncertainty. And sometimes they included damage uncertainty because there's a precision with which they know where all the buildings are. So if you know what the stage is, you're not necessarily sure if the building's above or below that, so you can include that uncertainty as well. So anyway, this is their attempt to do that. So
what's the damage if it doesn't get overtopped?
If it doesn't get overtopped, there's no damage.
Well, how come there's a dotted line that goes somewhere?
Oh, I thought, okay, so, okay, yeah, so Brian's asking me to remember exactly what I meant by this figure. As I think about it, here's what I think I meant. So here's stage, and here's damage, and as the stage goes up here, you're flooding more area as the stage goes up. As the stage goes up here, you're not flooding behind the levee, but you're flooding things that are maybe not protected by the levee and fringe areas. There could be some backwater effects that the levee, you flood behind the levee because you can't get rid of the water, and the pumps can do it. So the idea is here is the damages as a function of stage. If you built a levee, and this is without the levee, and I'm not sure that's consistent with what it says here. I shouldn't distract myself, but I gotta tell you, when I was at HEC, where they did all this work in 2005 on sabbatical, we had a 10-year flood, and they said, you've gotta go north of Sacramento and look inside the levees. And they have a series of houses that are built between the Sacramento River and the levee. And so I talked to these people. They had a beautiful little brick building. It was a house that was a little bit down from the levee. They told me about how in '86 the water got up to here, but it's brick. It's really easy to wash out afterwards. And they have, 6 hours of warning before the flood gets there. So there's plenty of time to take all the furniture and put them up on top of the levee.
Do they have insurance?
No, I don't think they have insurance. But that the 10-year flood only happens, and they actually were underwater in the 10-year flood. And the rest of the time, they have this wonderful property right on the Sacramento River, and they've got the swings out there. I went next door, walked over next door, and their house was down lower, and they were a mess, but they still built in front of the levee. Then I went to the third house. He was great. He had his house up on stilts, and so the water would come up. So his bottom of his house was just a little bit above the levee. But I admire those people. They knew they were at flood risk. And they, for the most part, were prepared to take that risk and weren't asking for a gift. What scared me was the people on the back side of the levee who thought that they were out of the floodplain and they didn't have to worry. And I'll show you a picture of the Thomas later, but those people I was really worried about. But anyway, so if I answer your question, Brian?
Yes.
Good. So this is the paradigm. If we have an analysis like this and someone says, okay, that's great, what do you mean by uncertainty? And for me, the uncertainty is this, and that, and they actually threw uncertainty into where houses were, and I just didn't seem much of the work to me. But anyway, so the traditional hydrologic risk is the variability in floods from year to year, and we have to keep that in expectation. But then we're worried about the uncertainty of the parameters that describe that risk. There's variability and uncertainty in discharge stage relationships. And is that variability from year to year, or is that uncertainty because we don't know the parameters of the levee? And they that stage discharge, and they had a deterministic stage discharge, but then added uncertainty to it. Levee freeboard was replaced by this probabilistic description of levee performance, and so that was all variability, but not uncertainty. And then there was uncertainty in the stage discharge relationships because they were fixed curves, but then they added uncertainty due to knowing, for the most part, where the buildings were in some elevations. And then there was variability they included in the operating assumptions, but not uncertainty. And all this matters because they would turn the crank and generate a description of expected damages, and then turn the crank on the uncertainties and say, and that's our uncertainty in that number. So the uncertainty in that number depended on what you called uncertainty versus variability, which was in the expectation. So natural variability and knowledge uncertainty. Certainly the flood that occurs every year is variability. There's lots of places where we can see that: maximum rainfall, temperature, dew point, moisture, sometimes called aleatory, which has to do with the rolling dice in Greek. And so you see those terms. Knowledge uncertainty is sort of the parameter uncertainty I'm being called. It calls epistemic uncertainty from the Greek. And here there's three versions of it. One is parameter uncertainty, which means I have the right model, I just don't know what the parameters are. Model uncertainty is I'm not sure I've got the right model for like routing flows. And then decision uncertainty says I don't really know what the objectives are, the discount rate, or something else. And so this is a taxonomy of variability and uncertainty. And for these studies, it's certainly important because they compute the expectation over all the variability and then ask how certain that is because of limitations of knowledge uncertainty. So all of these things that are varying and uncertain have to get sorted into one of these two classifications. So our 95 report, looking at all the stuff they were doing, sort of said, okay, here's what you ought to report, and I just today put national metrics. So referring to the Corps of Engineers, who's evaluating this project and trying to tell Congress whether or not they should build something and at what amount, and also the locals what they should build at what amount. It's what is the probability that target areas are flooded, and so that's going to be the annual failure probability. And we recommended that they do that without including uncertainty, because we didn't think they knew how to do it. I still don't. Do economic parameters justify proposed projects? And so the Corps of Engineers computes the expected annual damages, and we suggested they did that without uncertainty because, again, we weren't convinced that they were going to get the uncertainty distributions right, and if they're too heavy in the tails, then they could end up justifying economic decisions by using bad models. And then we like the idea of a description of the uncertainty in the economic analysis. So you've done this economic analysis without uncertainty, the risk analysis without uncertainty. Now tell us how accurate those numbers are. And system reliability indices are useful in design certification. So things like, what's the reliability if the 100-year flood happens, if the levees contain it? We thought that was good for design. We weren't convinced that the public was going to understand that. Now, they did not take our advice. They threw all this uncertainty and variability into the pot and used that to compute both economic benefits with uncertainty and risk of flooding with uncertainty, and called that annual exceedance probability of the exceedance referring to the capacity of the system. And that's what they're using, and they're the Corps of Engineers, so they do what they want to do. But we didn't recommend that. Project selection should be determined by the economic evaluation of alternatives. That's what happens when the federal government says it's going to highly subsidize flood protection works, is they're looking from a national point of view and saying, is the money we put into this project generate benefits that exceed that? Sometimes they like to see a 2-to-1 benefit. And that's important because the government should be fairly risk averse. It's, this is one project of many, and so you don't get into this stuff about what's your attitude towards risk that an individual would happen. The federal government should be averaging over lots of projects. So, and the best estimate of risk of flooding is of great interest to the public and public officials. So that's what we talked about. Now this section was my efforts to demonstrate with my students that throwing uncertainty into the pot was not necessarily going to result in better economic decisions. And I fear I'm going to confuse everybody because everybody's confused on this one. I never was good at explaining this to the Corps of Engineers. I'll tell you a story. This is an important one. I'm at HEC, Hydrologic Engineering Center in Davis, California, which is the research lab for the Corps of Engineers that did all this. And I went out there on sabbatical in 2005, which is after most of this happened. And I thought I was going to work on reservoir optimization, and they said, hey, how about we look at the recommendations in the 2000 NRC report? Maybe we should implement some of those. So it's only been 5 years, and I was on the report. So I said, sure, which I was glad to do. But to really do parameter uncertainty correctly, you need to use Bayesian statistics. Bayesian statistics is the way of describing unknown parameters by probability distributions and doing everything right. Classical statistics, traditional statistics, uses confidence intervals which do what they're supposed to do, but they really don't describe uncertainty right. Well, everybody out there was a civil engineer, and most of them had taken one course in probability and statistics as an undergraduate, probably a 3-credit course, and they probably left with a B or C and hoped they never saw probability and statistics again. Bayesian statistics is sort of like the 3rd course in probability and statistics. So from my point of view is, how am I supposed to talk to these people who are bright people, but sort of don't have the background? It's sort of like going in and talking about fluid mechanics for people who've had algebra. And so that's why I say I've had so much trouble with this topic. But anyway, do we have to worry about the fitted flood frequency distribution? And so this is an extreme case, but a sample of size 30, Beth Faber at the Corps generated lots of samples of size 30 and fit flood frequency distributions to it. So that the original record's based on Wappinger Falls here in New York. And the green lines are all of the, and there's some blue ones in there, the fitted log Pearson type 3 she got by using different 20-year records, all of which were equally probable given the lavender line, which was actually the historical record. And what you see is there's a huge amount of variability here in the 100-year flood. So the 1 percentile should give us a 100-year flood, and so that number is going to be somewhere between 6,000 and 30,000, which is a huge range. And so the feeling is, wow, when you have that much uncertainty in knowing what the true risk is, maybe we should take it into account. If you have a 60-year record, things are tighter, but still there's a huge variability in what you'd estimate to be the 1 percentile. So note what I'm doing is I'm fixing the risk and then looking at what the quantile could be and seeing there's a lot of uncertainty. Things worked much better over here in the middle. and they completely fall apart if you get up to a risk of 1 in 500.
And the y-axis units
Is logs.
Right. But so people know that.
Just you want to point that out that those were logs, right? So these were really bad.
And basically just that it's stream flow in cubic feet per second. So.
Well, the peak floods in cubic feet per second.
Right.
Go ahead.
I'm just saying people might not know what CFS means.
Ah, cubic feet per second. All right. Anything else I should explain while we're here? So this is the estimated exceedance probability of the particular flow, and this is the return period. So 1% exceedance probability is a 100-year return period. A 0.02% exceedance probability is the 500-year flood. So, okay, so we've got this uncertainty in the fitted parameters of the estimated parameters of the flood distribution, so what are we going to do about it? Well, this has been an argument in the literature, and this is sort of from a research talk, but Arnell considered 3 hydrologic risk estimators in a paper he wrote, and we followed up on that. And one was you take the historical record of floods and you compute the mean and the variance, and then you fit basically a normal distribution to the logs, and that's our traditional method of moments estimator. The Corps of Engineers, starting probably back in the 60s, used something they called the expected probability estimator, and that was supposed to take into account uncertainty, and the feeling was, at least on their part, that that was a better estimator. And then there's also an expected damage estimator that some other people were using, and that was sort of the way they were originally including parameter uncertainty. And so the question was, and he wrote a paper comparing these 3. Now this is cute. He wrote a paper and in Monte Carlo compared these 3. I then wrote a paper and showed the last 2 were the same. But the way he did the Monte Carlo analysis, he got different numbers, and so he just decided they were close to each other. But so we're going to take the floods Q, and we're going to take the logarithms, and let's call them X, and assume the X's are normally distributed. That turns out to be a fairly good model for floods, actually. And so we have a random sample here, Xi in brackets, and we're going to assume the Xi's are originally distributed normal with a mean mu and a variance sigma squared. And the first thing we do when we get our record is we have to estimate mu and sigma squared. So M, this notes the sample mean of the X's, and that'll be our estimator of mu. And S, which is the sample standard deviation of the X's, that'll be our estimate of sigma squared, and here's the formulas for those 2. So that's the traditional method of moment estimator for the logs of Q, the Xi's, and that's also the maximum likelihood estimators. And so that looks good, and we'll go with that. This is just sort of giving some description of what's going to happen because of that. So we're going to model the X distribution as normal with mean mu and M and variance S squared, because we don't know mu and sigma, and that's equivalent to saying that X minus M over S is going to be standard normal, 0 mean and unit variance. And then this last line just tells you how, in a Monte Carlo simulation, we generate possible X's. We generate a standard normal random variable Z, and then we scale it by S and add M, and that's going to end up generating X's that are going to have a mean of M and a variance of S squared. So that's sort of standard stuff. This expected moment estimator that was used for a couple decades for the Corps of Engineers tried to take into account that they thought that the method of moments estimator was biased and underestimated flood risk because it didn't include parameter uncertainty. And so the expected probability estimator is based on the following statement, which is correct. It says, well, if I think of M and S as random, then if I take X and subtract M, which is an estimate of mu, actually X has a mean of mu and M has a mean of mu, M is the average, and then I divide by S, which is not sigma, but looks sort of like sigma, and it turns out X has a variance of sigma squared, and M has a variance of sigma squared over N. So this denominator here corrects for the fact that X is random and M is random, but M has a much smaller variance because it's a sample average, and both have a variance that depends on S. And this whole thing turns out to be student T distribution. The mean cancels out because these 2 have the same mean. These have a variance that's proportional to sigma squared, and S squared in expectation looks like sigma squared. So this is your standard T value. It's like confidence intervals for the mean, except now it's a confidence interval for a future observation computed around the sample average of the historical record. And so the core like this. It says, okay, by using this distribution, we're taking into account the uncertainty in M, that's the 1 over n, and the uncertainty in the S is because we're using a T with n minus 1 degrees of freedom rather than a normal distribution. And so when in Monte Carlo simulation, they're going to generate possible floods, they're going to generate floods as a student T distribution, and that line should not go over the T. Times the square root of 1 plus 1 over n. The 1 over n captures the uncertainty in M, and then there's an S here, and the uncertainty in the S is captured by the variance of T, which is bigger than a Z, and this just notes down here that the variance of X minus M is the variance of X, which is a future observation, the variance of M, which is the average of past observations, and so that's sigma squared plus sigma squared over n is sigma squared times 1 plus 1 over n, and there you have it. Is that a better idea? Should we use that model for flood risk? Because it takes into account the uncertainty in the fact that the M is not perfect, and it takes into account that S is not perfect by using a T, which has thicker tails than a normal distribution. Is that good? You saw all the uncertainty, right? We want to take uncertainty into account. The core did this for at least 20 years, maybe 30. Let's not guess. That could be embarrassing. Is this good? We now are including parameter uncertainty. Shouldn't we do that? Don't you think we should include parameter uncertainty, John? Yes. Right. Well, it's perfect, right? I mean, that's true. So, all right. Well, here's our expected probability estimator. So I just want to note now, it is the case that if I unfold that statement, that a future observation will be greater than M plus S times this square root times a T at the 1 percentile, 1% of the time. If I take a bucket of paint and compute that with M and S being random, and I go out and I paint on the hillside a red line, and I do that lots of places with different M's and S's, it turns out that that red line on average across all those sites will be exceeded 1% of the time. So that looks good. So instead of estimating the 100-year flood as M plus S times a Z, that shouldn't be N minus 1. That should be 0.01 there. That's not in degrees of freedom. But anyway, so instead of saying the 100-year flood is the mean plus the standard deviation times the 100-year, the 1 percentile, the standard normal distribution, I'm going to use this, and it's going to be correct if I average over the distribution for M and S and all future floods. So the Corps of Engineers called this the expected probability estimator because the expected probability is now correct if I integrate over possible future values of X, possible values of M, and possible values of S. So you know, any place in the world that has a fixed mu and sigma, you imagine generating records that are going to have M's and S's that are going to vary, and future floods X, and on average over all the M's and S's you can compute and all the X's that would occur, we're in great shape. So they like that. They were very pleased. And then when the Corps was proposing to do this risk and uncertainty analysis, a bunch of papers in the literature talked about an expected damage estimator. And if you remember when I had the graph up and I said, see, here's a 1 percentile and there's this distribution of what the Q is that goes with that. They said, well, when we try to integrate over probability, the flow that occurs and the damages, we're not going to pick one Q for every probability. We're going to look at that distribution of what Q might be that goes with that P. And so when we try to compute expected damages, we're going to take into account that uncertainty. And if you do that with the classical confidence intervals for the quantile, and you do everything right, I proved in a paper we wrote here that you get the same thing, that expected probability and this computation, which integrates over P, then for every P it integrates over the distribution of what the Q could be given the classical uncertainty distribution, and you multiply by damages and you get the same thing. So from 3 we went down to 2. We just have to worry about whether we really want to use either the expected damage estimator or the expected probability estimator, and I don't have to argue about the others, and that's the paper where I showed that came out to be the same. So anyway, is that a good idea to include uncertainty? Well, all right, let's look at it. So I made up a simple example and said, well, let's consider the following. I have a house over here that's made out of sugar, and if it gets wet, it dissolves and it's gone. So I have to compute the expected damages for this particular house, which may be part of a neighborhood. And so the damages are 0 until the flow gets up to this little q, and little q is where the house of sugar gets wet and melts. And I want to look at these two methods we have of estimating flood risk, one without uncertainty and one the expected probability estimator with uncertainty, and see which of them is going to do a better job of estimating the damages to my sugar house. Last chance to vote. Anybody want to say who's going to be better? Will either of them underestimate the risk of this house getting flooded? Now note that the damages to this house are just going to be D times the probability I assign to the house getting wet. So when I fit these distributions, do you think they're going to overestimate the probability the house gets wet or underestimate the house gets wet? Well, I apologize, the graphs aren't going to be very good. So here's a expected damage estimator. D is expected damages, which is the cost D times the probability to get wet, and that used to be a script D, but we lost the script. And so, and then this, I want the probability here that I assign to Q being bigger than little q, and that's 1 minus the standard normal CDF evaluated at log Q minus my estimate mean. Well, this is the true value. I'm going to have to not use mu and sigma, I don't know them. This is my estimator, I'm going to stick M and S in there. So my estimate of the damages is going to be D times my estimate of the probability the house gets wet, and that's going to depend on M and S over here. So those are random, they're not fixed values, and I'm going to have to figure out what the performance is of this estimator. And so here it is. I plotted on the horizontal axis, that I hope people can see this. A student did it a long time ago. But here's the sample size, and over here I have the ratio of the exceedance probability to the true value, and we did it for a couple of cases here. So here is the triangles are when I'm estimating the 99 percentile, 1% exceedance probability. So this is the rate, the expected value of the ratio of the estimated exceedance probability to the true exceedance probability. If we go back here to, actually if you look at 16, then the triangle turns out to be about twice. So what we see is the method of moments always overestimates the probability the house gets flooded. It's really bad here for 0.002, the 500-year event. For the 100-year event, the triangles, it's substantially bigger, but it pretty much behaves itself after 50. And if we go down to the 10 percentile of the circles, we don't have much trouble. But method of moments, just using the sample average and sample variance and estimating the probability my little house gets wet, it overestimates the probability. Now, if instead of just plugging in M and S and use a normal distribution, I plug in M and then multiply by the square root of 1 plus 1 over M and use a T distribution to describe the tails, I'm upping the variance of my approximation, I'm giving it thicker tails, so it's going to think that this risk is much higher, and so here's what you get with the expected probability estimator. So now if we have the 100-year flood here, the triangles, you can see that it's it's a much larger over bias in estimating the probability my house gets wet. By taking parameter uncertainty into account, I've thickened the tails and things are not going well. And I put them on the same graph so you can see them, but they're still too small. But the conclusions of Gould and Arnell and Stedinger, all methods overestimate the expected annual damages, particularly when damages commence in frequent events. But the conventional method of moments is least biased. Although the degree of difference varies with damage functions, the results clearly show that use of either expected probabilities or expected damages, you didn't know they were the same, method would produce very biased estimates of expected damages. So including parameter uncertainty into the expected damage calculation increases a bias we already had. And here's my attempt to explain why that is. So suppose the 100-year flood is right here, and it gets 1,000, it gets mapped into 1% over there. And this is the true frequency curve. Now what happens when I estimate the parameters? I'm not going to really be using the true frequency curve. I'm going to get something like the blue lines. I may get a line that's to the left, and I may get a line to the right. And when I get a line to the left, then I'm going to estimate the exceedance probability of my house, which is sitting at 1,000 CFS, is something over here. And if I get a line to the right, then I'm going to overestimate it. Well, it turns out if you're talking about an exceedance probability of 1%, how much can you underestimate 1% by?
About 1%.
About 1%. That's the worst you can do. If it's 1%, how much can you overestimate by? 1%, 2%, 3%. So it turns out this distribution is very asymmetric. You can't underestimate by much, but you can overestimate by a lot. So when you average these, you end up with an overestimate on average. The 1%, the flood that house that gets exceeded 1% of the time, you're going to say perhaps 1.5 or 2, depending on the sample size. Now, this is related to the design event and a related issue, which is me going out and painting a line on the side of a building or the wall. Now, there's a real difference here. One is the house is fixed, and I want the probability that fixed house gets flooded, and that's this one. 1,000 was fixed. Now I'm going to go out and paint a line on the side, so the line is where I draw it. And so this is interesting what happens here. So I want to estimate the 100-year flood, and I want to draw a line. And so the distribution of m plus 2.33, that's the z I need, times s, that's my 100-year flood estimate. And it turns out it's going to sort of be distributed like this, about the true value. But then when you average it with the exceedance probabilities for all the estimates you're going to get, it turns out that the average exceedance probability of the 100-year flood estimate you're going to give is bigger than 100. It's sort of the same argument. And people didn't like that. The Corps of Engineers didn't like the fact that their 100-year flood estimates would be exceeded more than 1% of the time. So the expected probability estimator looks like this. And now it turns out that if this is the distribution of your 100-year flood estimator, with the 1 plus 1 over n and the t in here, it turns out that distribution will generate lines on the side of the stream that will be exceeded 1% of the time. So we got rid of the bias in our 100-year flood estimates being exceeded by upping the variance here and thickening the tails, but we made our bias in the damages we ascribed to a fixed house worse. So there are two biases. When we randomly drew a line on the wall, it got exceeded too often, so we raised it higher, but it used to be there was a house there, and it got too much, our estimate of its damage frequency was too high, but when we solved this line problem, we made the problem assigned to the house worse. And so the traditional method of moments has a modest bias in the exceedance probability, but in a T-year flood is exceeded too often. Expected probability has a much larger bias in the exceedance probability for a fixed house, but it solves the exceedance probability when we get to draw the line where we want. And that creates problems, and what problem do we want to solve? And this is actually the distribution of the exceedance probability assigned to that fixed house, where the house is at the 10, 1, and 10 percentile. And you can see, well, these are probabilities, not percentiles, but if the house is at the 10-year flood, this is a distribution normalized that we would be assigned the probability to it getting wet with a sample size 50. And you can see with a 10 percentile, the estimated probability divided by the true probability is about 1, where for the 1,000-year flood, it's like we have no idea what's going on. So that's the whole issue about whether we should have parameter uncertainty. The arguments reflect different philosophies, different views about how to use the log normal or a log Pearson type 3 distribution with available data to represent flood risk due to hydrologic variability and parameter uncertainty. While such philosophical differences are important to their proponents, including the author, I can get really wound up about this. Changes in the resulting flood contiles and flood damages are actually relatively modest compared to the precision, and that's this one. I mean, we're talking about bias, but then when you look here at the range in the possible estimates of the exceedance probability that are going to be assigned to that house, I mean, here's where you're overestimating the risk by 2, here's by 3, here's by 50%. With 50 years of data, you can't figure out if the risk is 1% or 2% or 0.5%. It's just not enough data. You're really out in the tails. So uncertainty seems important, but our attempts to just pump it into the analysis are going to distort our mean estimates. So I'm not sure how to deal with that. So anyway, uncertainty design, here's one thing we tried to do. They were trying to tell us that by including parameter uncertainty, somehow when they reported that their net benefits were 15 million, but the standard error of that was 2 million. We would somehow know how to deal with that. So we tried to figure that out, and so here's some jokes about uncertainty analysis. Convictions are more dangerous foes of truth than lies, and the trouble with people is not what they don't know, but what they know that ain't so. But anyway, this is a setup we did to try to look at the impact of including uncertainty in design. So we're going to select a flow that maximizes the net benefits. The net benefits are really sort of the damages avoided minus the cost of building a levee or something else. The optimum is obtained when you take the derivative, and the marginal expected benefits are equal to the marginal cost. And we added a constraint. We said, well, if uncertainty is important, maybe when the Corps does this design, they're so concerned about uncertainty, they might want to add a constraint that said they want to make sure that there's a 95% probability that the last dollar they spent is recovered. Right? So instead of just saying we're going to maximize this equation or that equation and set these next equal to each other, it sort of implies that there's a 50% chance you're going to completely recover the last dollar. Now you could get more than you deserve or less than you reserve, but maybe the government doesn't want to take that risk. Does the federal government want to take that risk? Well, generally we argue, and I thought about this more later, is the federal government should be risk neutral, so as long as everything's working out, they want to do it. But if you have a limited budget, why you should be fooling around with money you barely get back? So we added this constraint to the analysis. Here's a picture of our town with the levee and the stream, and we assumed a bunch of reasonable numbers like that, and we assumed a lot of normal distribution and parameters, and anyway, and there's the cost and benefits, and so the optimum is going to be in here someplace, and so you're going to have to take a flood record, estimate the parameters. That allows you to estimate the expected damages, compare those with costs, and pick an optimal design. That's what the net benefits looks like if you really know what the flood risk looks like. So you can see right about here is the best design. What happens if I over-design a little bit? What happens to my marginal net benefits? Nothing, because it's flat on top. So it sort of says small errors, you have a bigger levy, but you get more benefits. You have a smaller levy, you have small benefits. So the nice thing about optimums is it says it's flat, so little errors shouldn't cost you much. And so this is what we did. We had samples for flood risk were 25 years of record. The coefficient of the floods was 1, so that's reasonable, maybe a little high. Our decision rule was to use expected probability, to use method of moments, or we used a Bayesian rule, which is the right thing to do, and we added the probability that we wanted to make sure that here's the rule right there, that the value, the probability you recovered the last dollar was at least 95%. We started with 50%, 75%, 85%, 90%. What probability should we use for the reliability to recover the last dollar spent? Well, it gave us a bunch of decision rules. Here was that when we Monte Carlo this, the best design was, here's the design flow we picked over the true 1 percentile, which is the optimal design. Method of moments on average gave us the right design. The standard deviation was 0.21. Optimal value is 1. The standard deviation of the design we picked was 0.21. 20%. I mean, our designs are all over the map. The expected probability beefed up the tails, so it, on average, had a design was 7% too big, but the standard deviation was 22. I'm not sure 7% is a big deal when you got a standard deviation of 22. We put in here our expected probability estimator with these different reliabilities. Adding the reliabilities meant we went with smaller designs, so we were more sure we were going to recover the damages. The standard deviations are still pathetic. Here's the net benefits that we got, and the Bayesian algorithm threw a little regional information in, so it does better. But what's amazing in here is if you go out that requiring 85% reliability for the last dollar spent, you hardly give up anything on expected benefits. I mean, you're adding a constraint that makes sure that you're not going to spend money just because it looks like you're going to return it. So we can end up decreasing the size of our project by 15%, losing almost nothing, and being more comfortable that we didn't spend money that we were just barely recovering. So benefit cost ratio was always greater than 1 for the whole project, and some other things. So anyway, so we can conclude that uncertainty is not important. it can be we can be highly confident the net benefit is always greater than 0 and the benefit cost ratio is greater than 1. But what about the last dollar spent? And so this just shows us again that here's the net benefits from our project. Over here is a function of the different decision rules, and basically they're all doing about the same. So anyway, we also looked at, here's the statistics on the last dollar spent. So here's the incremental net benefits from the last 10% that you invested, and it turned out with method of moments, on average you lost money on the last 10% invested, and -6 was the mean, but the standard deviation was 90, so that's probably just 0. If we went down here and required 85% reliability, that we recovered the last dollar, then it turns out that the incremental benefits from the last 10% of the project are 50 and the standard deviation is 45. Is this what we want to do by including parameter uncertainty in our infrastructure design? You want to include parameter uncertainty in infrastructure design, what are you going to do with it? Are you just going to compute the expected value and bias that upwards, or do we want to talk about the reliability of infrastructure and say, gee, I don't know what the right parameters are for my flood distribution, so I'm going to add a reliability constraint that I recover my money? Is this helping?
What happens when somebody sues you because they think you skimmed a bit on design because you weren't going to recover that
I'm
last
the Corps of
dollar?
Engineers. You don't sue the Corps of Engineers. They're following federal policy, and they get sued anyway. But I don't know. I'm not convinced. This is a fun paper, but I'm not sure at the end of the day we know what we want to do. Other than it says that, gee, you know, if you're right at the top and optimizing, then a little less you don't lose a lot of expected benefits by building a little smaller. So, and we generate a lot of stuff. This was a nice master's thesis. From a safety point of view, could address reliability of residual risk targets, would require bigger projects or other flood risk management actions. In practice, actually, if you go to a community, right, it's terrible. You go to a community and you say, what do you think about this? And what they say is, how much is my flood insurance going to cost me? Aren't you worried about getting flooded? No, that's an act of God, it won't happen. But flood insurance happens. It's like death and taxes, right? Taxes happen and they're not planning to die in a flood. So it is just pathetic. People can't come to grips with the fact that these things could happen. Clearly, individual floodplain residents, local communities, and the federal government have different views towards residual risk and uncertainty and returns on public investments. And you should argue the federal government is risk neutral, and so they shouldn't care about this, and locals could, because they're being forced to invest in this project. And now here's an interesting thing. Suppose I build that project. The levee's there, it's polished, it's gold. When do I get benefits from that levee? Do they happen every year? How do I compute the benefits from a levee? What computation determines the benefits from the levee? Yes?
Reduction in damages?
Flood damages that aren't produced. So if I build that levee and there's not a flood that year, are there any benefits? No. If I build that levee and in the next 25 years, there's never a flood where I needed that levee, were there any benefits? So if you want to talk about uncertain benefits, are the uncertain benefits because I'm not quite sure what the parameters of the flood distribution are, or because I don't know if there's going to be a flood at all? Or 2 floods. It could be that that levee stops 2 floods from sorting the area. So when the federal guys at HEC and Davis are there, they're talking about uncertainty is important. We've got to make sure we've got exactly what the distribution is of our uncertainty and the net benefits, because we want to get that right. And I'm thinking about, you want to talk about uncertainty, let's talk about whether there's any benefits to this levee at all, or whether there's huge benefits because you stopped 2 floods. And that all went away because that was variability and we averaged over that. Was that the right thing to do? And when you start talking about whether things are variability and we average over them, they're uncertainty, and we put them in the uncertainty distribution, then you're saying, from somebody's point of view, probably the feds, that we're concerned about that uncertainty because we might make the wrong decision, but we're not worried about whether there are actually any floods in the 25 years. We've decided we're going to average over that, but we're really concerned that we might have built the levee a little too big or too small because of uncertainty flood distribution. So anyway, it's, I don't know, no one knows the answer to these questions, which made this very frustrating research. Overall, the experiment indicates that for realistic situations and reasonable models of hydrologic risk, water resources managers should be able to identify flood risk management projects that will improve the public welfare, though there's a huge amount of variability in what's going to happen. However, for reasonable record lengths, the true optimal design flood cannot be determined with much precision, and there will be significant uncertainty in project benefits. But averaging over lots of projects, the federal government should be happy. But quantifying this uncertainty should be possible to make better decisions, right? By describing the uncertainty and the expected benefits, we can make better decisions. Was this analysis said that I could make better decisions here by knowing what the uncertainty was so I could add a constraint, or should I have just used the method of moments and forgot about the uncertainty analysis altogether? Right? I mean, do we just go with that and ignore uncertainty? Do we go with expected probability and include uncertainty? Because that only cost us money. That didn't help, and here I'm including uncertainty, and I'm building smaller projects because I want more reliability, but I don't know, does this get me any place? Now you're wishing you hadn't come, right? All right, well, I've got very few minutes left. The American River Project in '85 and in the second NRC report in '99 were about Natomas and vulnerability in politics, and so I like to throw that in. This is just really pathetic. So here's the city of Sacramento, and they built it in the 50s, that's Folsom in the 50s. There's where Auburn was going to be built as a second reservoir. Sacramento has a risk of flooding now. Our best estimate is about 1 in 60. To have the capital of the state with that sort of flood risk, I mean, the Sacramento Bee, when I was out there in 2005, sort of printed the floodplain maps on the paper, you know. Here's the 7 feet of water that the capital will be sitting in. The steps are high, so the capital will be okay, but you'll have to swim to get there. The idea of paralyzing the capital of Sacramento, California, Sacramento, seemed crazy. We were arguing about the Natomas area here. Natomas used to be a lake. They pumped it out, and it's now ringed by levees. And I think there's 500,000 or 1 million people who live in there. The sports arena's there, and the I-5 goes through there. And so one of the big arguments was how good those levees are. The city of Sacramento, the downtown areas will go under, but the other areas are higher. And so the question was what we should do. And I was just appalled that they want to put levees around Natomas and put 500,000 to 1 million people in there. It sounded like New Orleans to me. Of course, this was sort of before New Orleans, but I mean, anybody who knew what was going to happen knew with New Orleans was going to go underwater. Only the people who lived there sort of were surprised. So Natomas is the same thing, and that's where I told you. I went on the levees, and I was up here, and I was looking over the backside at all the people in Natomas. I was at HEC in 2005, and they hired a new person who came in from Washington, whose job it was to liaison between the Corps and FEMA and other people to explain flood risk. And she got there and said, "So good to see you. Where are you living?" She was in Natomas! How can you, whose job it is to explain flood risk to people, be living in Natomas? And she said, I asked them if I was in the floodplain, and they said no. Because she's protected by a levee that's rated to be the 100-year flood, so she is not in the floodplain. This is what happens if the levees break. Normally, when the levees break, it's deepest at the levee and the hill goes uphill, right? So if you run fast enough, you're okay. In this case, it gets deeper in the middle. I said to the lawyer of SAFCA, the Sacramento Flood, whatever they are, how in your good conscience be trying to get these levees certified so you can put 500,000 to 1 million people in there and make all kinds of money? Because, look at 23 feet. Anybody here 23 feet high? Can you escape a flood by getting on the roof if the water's 23 feet? How tall is your roof? Now, one city councilman said her approach to flood risk management was a raft on every roof. But this is terrible. I got him to put this picture in the report. It's like, don't you guys realize what you're doing? Now, if this is 100-year flood protection, and a house lasts 50 years, what's the probability that house experiences a flood? 100-year protection, 100-year protection. I mean, that's rare. It's not going to happen, right? And your house is there 50 years, what's the probability it gets flooded? 40%! Now, 40% is a real number. 1% may not happen, but 40% is starting to look big. Well, the SAFCA attorney, when I said that, said, don't worry about it. These levees are higher than the ones on the Sacramento side. The city of Sacramento is underwater first. And we'll be okay. Anybody got a problem with that argument? What happens after you put 1 million people, if they're in the city of Sacramento, upgrades their levees? Then you're the first one to go underwater. Well, anyway. So I wrote this in the report in '95, and complained to the Corps about some stuff they did, and they said, well, we reproduced your text directly in our report. Should the levees protecting Sacramento, south of the American River, be threatened? Residents could attempt to move to higher ground to the south and west, further away from the river, and the depth of flooding would generally not exceed that at the river's edge. Few areas would experience flooding of more than 10 feet. So if you can swim in 10 feet of water, you're fine. Natomas, on the other hand, is ringed by levees so that residents trying to leave the area would have to find their way across transportation links to areas with higher ground, primarily to the west. That's on I-5, and really it's I-5 because the river's there. You've got to take the bridge over I-5. Moreover, because Natomas is a depression, 2/3 of the area would experience flooding over 10 feet, and some areas as much as 35 feet in depth. If the Natomas area is subject to a risk of 1 in 100 being flooded in any year, the probability of at least one flood in 50 years is 40%. See, I worked that out. That's how come I knew. Thus, the probability of a relatively catastrophic event within the lifetime of most residents is roughly equal to the probability of flipping a fair coin and getting hits. Flood risk management. And so I was trying to contrast the vulnerability between the typical levee failure where you can run away and visit your neighbor and this one where you can drown, because they're not all going to get on I-5 and get out of there, even though they have some warning. And so there was some stuff about deep floodplains that the government was dealing with, and can people escape, and some idea, the idea of just what's your risk of flooding. It's not just your risk of flooding. What's your ability to escape? Is it a flash flood and you won't get out of the front room? Is it something where you can just wade up the hill a little bit and stay with your neighbor? Or is it Natomas where you're lucky to only get 10 feet of flooding because you're next to the levee? Of course, there you got the flood burst. But if you're in the middle where you don't have the flood burst, you can go to 25 feet. And I was upset. And so this is actually the Sacramento Bee. By putting Natomas first, SAFCA, that's who the attorney worked for, has given new currency to the slander that Sacramento officials aren't nearly as concerned about the 400,000 lives that are at risk there as they are about the real estate schemes of some Natomas developers. And they were making a mint. They built the stadium over there, they had the freeway, they had some other major facility that hadn't been developed because it used to be a lake, and they were going to put these houses in there and make a mint, and I assume they were smart enough not to live there.
We gotta stop here, Jerry.
Excuse me?
We're getting over 5 minutes over time.
5 minutes overtime?
Yep.
Well, I always like Feynman, who said, for successful technology, reality must take precedence over public relations because nature can't be fooled. And I go, oh, well, okay. Thank you very much for having me.
People need to go, we can go, and if you want to stay and ask a question or two before the next class comes in, we have maybe five minutes or so. If anybody wants to not live in the Commons. Any other places we shouldn't live, Jerry?
New Orleans.
Yeah.
You know, you get people in New Orleans, and you say, we're stuck here, they live there. God gave us a gift and wiped them out.
Now they want to rebuild it.
And the mayor said they can't. The mayor said, I'm not going to tell people they can't rebuild. I mean, does God have to engrave the invitation? I mean, they wiped them out. Now's the time to say the 9th Ward, which is below sea level, is not the place to live. You're going to have a port there, and there's parts of New Orleans that are above sea level where things aren't so bad. But I mean, we are so stupid as a society, and I apologize to anybody from New Orleans. I've had people say that I'm insensitive to people who live in New Orleans. But it's just, you know, and I can play around with, I'm sorry, you know, it's like dancing angels on a pin talking about all this bias and stuff, because the issue is really not bias, it's variability, and it seems to be we're sort of okay there. But we just need to not live someplace. And that's why I like Galloway's comment. It's like, okay, let's look at what has to be there, and let's look at what doesn't have to be there, and in particular, let's not fool my friend who moved into the Sacramento area that she's out of the floodplain and she's safe in Natomas. Right. I mean, this is a woman whose job was to communicate flood risk to people, and she ended up living in Natomas. We almost strangled her. But she asked. She asked the questions, and she got the answers. You're not in the floodplain.
So who do you ask to get the real answer? Like, who has the real answer?
Who has the real answer?
I mean, like,
Can I not
who
give that?
told her it's not in the floodplain? Her realtor or her?
Yeah, the realtors, those
And
sorts of
then
people.
who would have?
Well, I mean, what you'd have to do is go to the FEMA maps and figure out that there are levees there, and therefore that place is not going to be colored as a floodplain because of the levees there, which is got to figure out a levee there and what the elevation is.
So it's on the consumer.
It's on the consumer. We had a guy down here from the Army Corps of Engineers at Buffalo office, and they'd had a flood, and he described it going around the community, putting up markers that said the flood was this high. But they all disappeared. The realtors took them down. Try to sell a house with a marker outside that said the flood was this high. It's a I don't want to use the word conspiracy because I don't really mean that, but it's all up and down the food chain. And I don't know what, I guess I'm really frustrated. One of my colleagues at HEC is frustrated about the fact they just talked about the 100-year floodplain. When behind a levee that sort of works, but even behind a levee, if the levee breaks, somebody's at the edge of the floodplain, we're talking about 6 inches, and somebody else is next to the levee, and it would be nice if more of these maps gave you a sense of the relative risk of where you were, whether it was behind a levee or whatever was going on. I don't know what the solution is. I think the solution is for Congress not to repeal laws that say we're not going to charge people the real cost of living there.
They haven't repealed it yet. They delayed the delay.
And so I applaud their not repealing that.
It will get repealed though.
Yeah.
Well, here's one that happened that I saw. When they reevaluated the levees, and I forgot if it was exactly to Thomas or Sacramento or one or the other, but they went back through and reevaluated them because they had an additional flood record and there had been a lot of floods. And it turned out they were no longer in the they were no longer out of the 100-year floodplain because the levees got downgraded because of the flood risk. So Congress passed a law that grandfathered them for like 10 years to be out of the 100-year floodplain because it wasn't their fault. Okay, well maybe it wasn't their fault they were living there, but that's the signal you're sending to people who are moving in.
Right.
It's like,
So that's the moral hazard view of insurance, right?
yeah. I mean, I like Feynman. You know, you can say the risk is anything you want, but nature is not paying attention to press releases.
So then, a couple of points, Jerry. One is about the length of the historic record. I mean, it just seems like you're always, whether it's flooding or drought, you're always going to be constrained by that. And even you were saying mu, you know, that the average represents mu, but if mu is, if the actual real mean is moving, if it's not stationary.
Okay, so climate
Yeah, I
change.
use that too.
You like that one?
Yeah,
Oh, I'm sorry.
I liked it.
The picture's bleak, gentlemen. The world's climates are changing, the mammals are taking over, and we all have a brain about the size of a walnut. Yeah, so the comment is,
I use that for bounded rationality.
Falcon rationality. Yeah, we got a problem that things are changing, but you know, they've been changing for a long time.
Exactly.
People have been changing the landscape, planting crops, letting forests come back, pumping the groundwater, channelizing things. So I'm not, when people say, oh, climate change, things are going to change, it's like, get on the train, you know, things have been changing for a long time.
And even without anthropogenic forcings, there's a lot of...
There's a lot of natural variability.
Right.
We can show you records where incredible things have happened and there doesn't seem to have been any change in the landscape.
Right.
But a lot of people who raise that, you know, maybe I'm wrong, but I can do the parameter uncertainty calculations, and those distributions are big, and people seem to want to completely ignore that. Like, but now the climate's going to change. Oh my goodness, we don't know what's going on. What makes you think we had any idea what's going on before?
I know.
There was all this uncertainty, we didn't know what was going on, so there's a little more uncertainty, you know?
Right.
Get used to it. Yeah, so it sounds like you're in the same boat.
Yeah.
And I don't know if this deals with the kind of infrastructure you want to talk about, but...
Well, I mean, we're talking about a lot of stuff.
But
it's
an
expensive,
issue of how do you
and
plan.
it's interesting.
Yeah.
And it gets into like the idea that you recommended something to an NRC, you know, panel or whatever it was, and they decided not to listen, is another aspect of one of the things we're trying to talk about, which is how do you get this information to actually integrate into decisions when you can give them the best information and you can never really account for the human factor.
This is the thing I can't imagine. The 2000 NRC report, which was supposed to really look at their analysis procedure, which was full of significant errors in how they calculated the probabilities. And as we were finishing that report, I was on sabbatical at the Army Corps of Engineers at IWR at Fort Belvoir. So I called the guy in Davis and said, you know, I'm on the same team. I'm sitting in the Corps office. Can you tell me that you're going to correct some of these obvious errors in the way you calculate probabilities so that I can tell my co-authors that we don't need to splatter your name in red ink across this report. And it's like, no, that's the way we do it, we're the Corps. And so, and then they just didn't do anything until I was out there in 2005, and then they said, hey, you're here, why don't we talk about this? And so I wrote 2 memos about what to change, and they said, no, that's too much work. The program's working. The program's working.
Yeah, there you go.
We're evaluating numbers, they're planning things, Congress is approving them, we're building them. What's your problem? Well, I guess I just don't understand what we're about here. But anyway, then in 2013, they called me and said, we are, they have a review, they send software now through to make sure it's doing the right thing, and they actually paid me money to provide a review of that software. And I said to, well, the other thing you have to understand is the woman who's now responsible for that software got a PhD with me. But anyway, I said to her, why are they asking me? Don't they know what I'm going to say? She said, that's okay, just say it. Because in some sense, she said to me quietly, and I have not told you her name, but that would be easy to figure out. It's sort of like, I've been complaining about that, but they haven't been willing to put the budget in to change that. And so, great, they actually paid me to tell them the same thing I've been telling them since '95. And I wrote it all out. But it was interesting because now there was a different organization that deals with risk analysis in the Corps that was evaluating whether HEC had this program right, when one of their official reviewers, not those people at NRC, but the official reviewer, sort of said there are these problems. They sort of took them seriously, like, oh, wow, okay, we can't get that in this version, but maybe in the next version we can make those corrections. So that's all 95, 20,
And we should clear out of here now because the next class is
Yeah.
coming in. Thank you, Jerry.